explain these?
Yeah, and you want the opposite. Because, like, it says that continuous is, like, on a number line, but
Yeah.
Yellowstone can't erupt at 0.5 times. So you can eat 0.5 pounds of sugar. So,
Guys, you're right. Yellowstone can only erupt a countable number of times. 1 time, 2 times, 3 times. That's discrete. That's what discrete means. They're actually both on number lines, but the discretes are the whole numbers.
okay, so he just put it's a whole number.
It's a whole number. They're countable.
They're countable.
They're countable. How many students in my class? 22. I can't have 22 and a half. How many pounds do they weigh? Well, together, they could weigh a half pound to quarter pounds in between. It's a continuous measurement, right? So continuous, you use your whole number line. Continuous is the whole number line. Okay. And that really kind of starts the beginning of the binomial part. Okay, this was a good place to start. This is your probability. To find your probability, it's the same as your relative frequency. It's part over whole. So we're going to add up the total of your frequencies. These are just the x values, just the name of the intensity of the hurricane. We're going to add up the whole thing and put part over total. 61 over 165. 39 over 165. And generally we go 3 decimals on a probability. Part over whole, not the intensity number. That's just the name of that hurricane. We have, all our hurricanes go from intensities 1 to 5. So for the past 100 years, they're listed here. Okay, now you don't have to worry about this column. We don't really, in case anybody did it that way, I don't really need you to do it that way though. I just need you to find the probabilities. This is the same as your relative frequency. Part over whole. And when you do, this is your probability distribution, this table. When you do your graph, it's the same as your relative frequency graph. Only a little easier in your graph is you're going to put all your x values along the bottom. These are your intensity numbers. You're going to give it a title. Okay? And your relative frequency. This is your P of x. Your probability. Think money. A nickel, a dime, 15, 20. Label that way. And it's going to be a relative frequency histogram. So it's going to have bars. Would you say this is symmetric? These bars? Nope. Where would you say the skew is? To the right. It follows the tail. Good. Now, from your table, you can answer some of these questions. This is the reason we make this probability distribution. Find the probability that a hurricane selected at random. If I pull up a random hurricane, has an intensity of at least 4, that means it could have 4 or it could have 5. So I've already calculated my probabilities for both. Just add them together. 0.085 plus 0.018. Just add them together. If I wanted to, I could add up 17 over 165 and get the same number. Use your chart once you have all your probabilities. What is the probability of having less than 3 intensity? Then I add up the 61 and 39 over 165. Or I already have their probabilities. I just add their probabilities. That's the beauty of your probability distribution. Okay, now to find your mean and your standard deviation, I don't know if you remember back, but we did this 2 ways. We did this in L1, L2, and did a one-bear stat because this is your frequency. And you came out with the mean. And in this case, you want the population standard deviation. And it even had out there a sample standard deviation. The second way to do it, wait, hang on one second. The second way to do it is L1, L2. Because you've already calculated your part over whole. The only problem with this is the sum of this is 1. So when you do this, it will not give you a sample standard deviation. Because when we find your standard deviations, I don't know if you remember back, when we did that whole big long table, we did your means, we did the difference in your means, we divide by n. In a sample, we divide by n minus 1. So I can't do a 1 minus 1 and get 0. So if you do L1, L2 with your probability, then you just don't get a sample standard deviation, which is fine. You only need the population standard deviation. That's the best way to do this. There's another way where you multiply this times this and get this. And if you take the sum, you get the mean. But it does not give you the standard deviation. So we looked at it way back in the time we did it, and then we just went right to the L1, L2. Much easier. Did you have a question, Angela?
Yeah, for the L1 and L2, I know you typed in 1, 2, 1 through 5 for L1 and L2. You typed in which one you want.
Well, I gave you two choices. I said you can do this L1, this L2, or you can do this L1, this L2. This always has to be L1. These are your X values. How we interpret this, when your mean comes back to be 2.1, it's kind of like when you get your average of your test scores. You have 10 tests, your average comes back to be 86. The average of all 10 tests is an 86. It's like your prediction. You will probably get an 86 on the next test. Thereabouts, to keep that average up. So the same thing when this mean comes back. The mean comes back to be 2.1. I look at the intensities, and I say, on the average, I have a hurricane with the intensity of about 2.1. I obviously don't see 2.1 there, but the same thing happens when you do your mean for your scores. Maybe it's not 86. Maybe it was 86.5, 86.7. It doesn't come out to be exactly. And our means are always 1 decimal more than our X values. So we could say it's approximately, on the average, a 2 intensity hurricane. But on the average, we say the mean is 1 decimal more than your X values. Okay? To kind of come back, the probabilities? No? Okay. Binomial distributions. This is a good one. This is another major one that we have. And a binomial means we have two choices, a success and a failure. And we can tell right away, this surgical procedure is being performed on 8 patients. You are told there's an 80% chance of success. So what's the only other thing that happens? Failure. So our N is 8, our P is 0.8, and our Q is 1 minus our P, 0.2. We're going to construct a binomial distribution. Whenever they say distribution, we're looking at a table. We want to know all the possibilities. If this doctor is doing 8 patients, he could have 0 success, 1 success, 2 success, 3 success, all the way up to 8. You can't have more than 8 because he's only performed this 8 times. Now, you have two choices to calculate your binomial probabilities. You could use the Algebra 2 method. At 8 things, I want 0 success. My success is 0.8. I want 0 of them. My failure is 0.2. I want 8 of them. That will give you this first one. Then you're going to change this to a 1, this to a 1, this to a 7. I want 1 success. I want 2 success. I want 3 success. Or, the other way we did this was in your calculator. We went to second VAERS, and this is not a normal PDF. What is it called? A binomial. So we come down to where we see the word binomial PDF. And we say number of trials, 8. P, probability of success, 80%, 0.8. My X, I'll start with my 0, and I paste. And I say, well, I know my probability cannot be greater than 1, so I look and see, oh, there's e to the negative 6. That means move my decimal 6 places to the left. I get 5 decimals, and I write it to a significant number. At this point, nobody should give me 2.56 as a probability. Now, easy way to get the next one, second enter. Go back and change it to a 1. Again, I can't have a probability greater than 1, but I notice the e to the negative 5. That's the 10 to the negative 5. Move my decimal 5 positions to the left, I get 4 decimals. And I just keep doing this until I exhaust my table. I just do this till I exhaust my table. And I keep changing that last number because the other two will stay the same, and it fills in my whole table. Generally, you could go 3 decimals, but make sure you have a significant number. You don't want to say it's 0 if it's not 0. You want to go to a significant number. Altogether, they will add up to 1. From this, you could make your graph as well. This is like your relative frequency here. This is like relative frequency. These are your x values. These are your relative frequencies. This is your p of x. And notice these are hardly anything here. Until we probably hit number 4. We get a little bit less than 0.05. Where's the skew to this curve?
It's skewed to the left.
Skewed to the left. And we like that skewed to the left because look where our successes are. And we would like to know that the surgery, yeah, you would like to go to a doctor that has good successes. You wouldn't want his surgery skewed to the right. Who? Oh my goodness.
How do you know it was population?
How did I know it was what?
Not to use that too.
Oh, these?
Yeah.
Well, when they ask for mean, median, and mode, you could do 2 things. I mean, mean and standard deviation. You could do L1, L2, because you only have 8 entries. On a binomial, we also have a series of formulas for you, and I put these on your formula sheet as well. The mean is n times p. The standard deviation, n times p times q. What generally happens is they'll ask you, like, say we perform this 250 times. On the average, what are his chances of success? So if you had to find the mean, you wouldn't want to make this table for 250 patients. So you would use these little formulas here. But because this table is small enough, you can certainly do your L1, L2.
What if it wasn't?
Then I would use those formulas. So like if it was on 250 patients, definitely use those formulas. Now from this table, what is the probability that the surgery is successful for exactly 2? Well, here's your 2. Here's my exactly 2. What is your probability that it's successful for fewer than 2? I don't want to count 2. I want to add these up. It's going to be very small. Don't forget, it's based on 8 still. It's based on 8. Then it only has fewer than 2 successes out of 8. So this has a lot going on in here. Everybody okay with this? I think, do you remember doing this now?
Yeah, it's just some of my values are a little off.
Yeah.
I'm still kind of stuck on what we just did.
The probability? Part over whole?
No, like the thing we just did, testing and stuff like that.
Oh, the hypothesis testing. Yeah. Well, that's like a different field. The hard part of going back to review is we're bringing you back to things before we weren't inferring. Well, actually, probability is a little inferential in here.
Are you gonna give us like those?
I'm going to give you the formula sheets. That's it. And the tables, of course. I gave you all the tables, and I'll give you the formula sheet.
I think the
But it's
hardest part is
perfect.
all remembering like the little stuff.
Mm-hmm.
Wait, can we go on to like probability? How did we do that?
You took it right off the table. We said if the probability is exactly 2, there it is. If it's fewer than 2, add those 2 up. If it's 5 or greater, add those up. Because you got all your probabilities there.
Do you have to do the 8 0?
Do you have to do, no, the C80? No, you can do this in the calculator instead.
Oh.
You have a choice, you could do it either way, they're both the same answer.
I'd rather just use the calc.
Yeah, I would just absolutely use calc, but you have to know how to use it because I'm not going to tell you on the final how to use it. Okay, these kind of go back to your basic z-scores. If you remember your z-scores, it's always area to the left. And on table 4, it shows you it's shaded to the left. So when I look up a z-score, I get the area to the left. And if you remember these way back, I was always big on sketching. Make sure you shade. Make sure you look to see what you're doing. So if I'm looking for the probability that a z-score is greater than negative 2.10, I'm looking for the area under the curve. Probability is area under the curve. So I need to sketch and find my area to the right. That's where I'm pointing. When I look this up in my table, I'm given this little piece right here. And I say, that can't be right because I want this whole big piece in here. Remember when I used to say judge by 50%, more than 50%, less than 50%? It's a good way to tell. I want more than 50%. I'm going to subtract it from 1. When I want the probability that it's less than 3.22, I look up 3.22, and it is the area to the left. When I look up in between, the in-between say subtract the areas, not the z-scores. Do you guys remember the calculator step for this? For those that like the calculator?
Yeah.
It's second there. We're in a normal PDF right now. This is a normal probability distribution.
Wasn't inverse
In second VAERS, normal PDF. So, hang on. Second VAERS, normal CDF. My cumulative. Now, if you use a z-score, I'm going to do the in-between one. There's my lower limit. This is my upper limit. I leave the mean and the standard deviation for a standard normal curve, 0 and 1. And I come down and I paste. And that takes my z-scores, find my areas, and subtract my areas. It's great for the in-between. If I do second VAERS, normal CDF, say I want this one, greater than 210, I have a lower limit and an upper limit. My lower limit is negative 2.1, 2.10. My upper limit is my 999. And then I paste. I don't know if you remember your upper limit and your lower limit. And if it's the upper limit and I need to get a lower limit, there's my negative 999. You obviously will never find these, but that's where we're going to set our limit to so that it gives us the total area.
Mm-hmm.
If you put an X value in, then you're going to change the mean and the standard deviation.
Let's say you were doing part D, how would you calculate since it's the one?
Part D, you can't. You'd have to do this part first and calculate it, then that part. Because on part D, you have to add these together. So you have to look up this one first, then you have to look up this one. Remember on an OR, if there's no overlap, you just add them. So I gave you this. This is an AND, because it's an in-between, and that's an OR that had nothing in common. And you would add them.
When would it have something in common?
Well, when you do this, an AND, not an OR. Oh, when it's an OR, if it does this, like say I do from here, and then I go from here, then I would have to say, I wouldn't give you one of those though. Now, the flip side of this guy is now when we give you the x values, and this might be what you probably remember working with, your z-score formula. So we say, I want to know the probability that your x value comes between here and here. If you sketch, guys, it's so much easier to see. And so you add 0.08. Add another 0.08. Add another 0.08. And then subtract your 0.08. So if I'm looking between 3.6 and 3.64 and 5.64, I know I'm out here somewhere, wherever this was. And I know I'm over here somewhere. I'm looking for a big chunk of area. It gives you a better feeling for what you're looking for. Find your z-scores. Subtract your z-scores.
If you use your calculator, like one of the
Well, if you use your calculator, yeah, of course, you have to tell me that you use your calculator because the rounding is always off. If you use your calculator for this, you use your x values in here. Pay attention, because if you remember this back, it's really a big help. If you're using x values, you have to change your mean. You have to change your standard deviation. And then you're going to paste. And you're going to get your answer. And it does everything else for you. It does your z-scores, it calculates everything for you. This kind of brings you way back. Let's take a look. Maybe this will kind of make more sense when we hit this one. This is a good one to do. Okay, we have a state test. All the Washington State public schools took a math assessment test. This is the population of all Washington State schools. They had a mean of 281 and a standard deviation of 34.4. Now, if we made a sketch of this, here's my 281. Even if I add 34, just get an approximate one. I didn't do it, but then you keep on adding up. Then you keep on adding down. You subtract down. It'll give you a better feel for where your scores go. So now, find the probability that a student had a score greater than 315. Here's my 315. Greater than, shade to the right. This will give you a better flavor for this. Remember when I had to always sketch and everybody's like, oh, I have to make a sketch? Yeah, the sketch really is really helpful. Take a minute, add your 34.4, subtract it down. You only have to do it once. And then you could use it for all of these. Between 250 and 305, well, 250 is here somewhere, 305 is here. I want this area. So I calculate my z-score, find my areas, subtract them. Probability is area under the curve. Probability is also percent. So this one too, find its probability. When you're looking for its percent, just move the decimal 2 places to the right when you find your area. That it's greater than 250, pretty good chunk is greater than 250. It's more than 50%. That's what your curve helps you too. So when you get an answer like 81, 82%, you say, it's area to my right. This one is used for like a prediction model, because probability is a great thing to make predictions with. What is the probability that this will happen? Based on the things that we saw, that's how we judge out what will happen in the future. If we have 2,000 that are selected at random to come into this program, or to take this test, or whatever took this test, how many would be expected to have a test score that is less than 300? Okay, less than 300, we can figure out what their probability is. Find it based on 2,000, and we'll know how many to expect to come into this program, into this test area. Good so far? I thought this one was a good one because it gave you pretty much everything. It gave you greater than, it gave you less than, it gave you in between, it gave you if n was there, it gave you the top 5, the bottom parts. So then you had to kind of transform your z-score. If I'm looking for what score would put my students in the top 5%, and this is how they do a lot of your SAT scores. If a college says, I want the top 5 of all my SAT scorers, they don't calculate each test in between. They take the mean, they take your standard deviation, they find your z-score associated with that area, 0.05, and they calculate the x value, that would be the cutoff. So if you don't reach that point, they don't look at your SATs. No, only to find this one. Only to find your z-score. There's no calculator step for this one. It's your same z-score formula, but it's just transformed to solve for x. It's the same thing, but there's no calculator step for it. You can do inverse norm just to find your z-score. What score would be in the lowest 25%? Again, you're going to use the x value, the lowest 25, find your z-score, plug it in, and you'll find your x value. Now, here's where we go to your central limit theorem. In a random sample of 60 students drawn from this population, what is the probability that the mean test score is greater than 300? This time, your standard deviation has to be divided by n. And it kind of tightens the field a little bit. So what is the probability that it will be greater than? It's approximately 0. Because it's way, way, way to the right-hand side. This is a good one to go through. However, you have had to do your review. Are there any questions on this one? This is a good, okay? Because this also deals with some of your binomials. In a survey of adults, 68% thought that DNA tests for identifying an individual were very reliable. They say reliable yes, reliable no. You randomly select 24 adults and ask them if he or she thinks that they are very reliable. Out of 24, your probability of success is 0.68, and minus 0.68, 0.32. We needed to decide whether this approximated a normal distribution, and we can use the rest of our rules. So we had to run 2 tests. N times P is greater than 5, and times Q is greater than 5. Because when their products were greater than 5, it made that table look like a normal curve. There's a little section in the book, and we did that little applet thing from Khan Academy that did a number of times to show you that it approximated the normal curve. Once we do that, the only how you could find your mean and your standard deviation is with these formulas. I have no L1 and L2 table to put in. I know my P, I know my Q, I know my N. So I use my formulas. Now, find the probability that at most 15 people say they are reliable. First of all, at most says this is the most or less. But because I have a binomial distribution, I have to correct for continuity. And if you remember how we did this, we laid these out a little bit. It went like 12, 13, 14. It stopped at 15. If it's an upper limit, I increase the upper limit by 0.5. If it's a lower limit, like we said, x is greater than or equal to 12, then I would drop the lower limit, 0.5. Okay?
And you can also use that in your calculator.
You can use that in your calculator too. You just have to correct for continuity first.
You type in
Nope, you're still on a normal. You're on a normal. Yes, you do the same thing you did for the above ones in here. 15.5.
Oh, that was
Lower is negative 999. Now be careful when you do the upper limits and the lower limit. If your values are obviously in the thousand, don't use 999 as a value. Use 99999 to keep stringing on the nines. Find your z-score for this, and then find your probability. Here was the biggest thing. Correction for continuity. That was the biggest thing. Your answers will be close, because obviously between 15.5 and 15 is not that big of a deal, but you still have to correct for continuity.